Here's a box. You feed it 3 bits and it hands back a single bit, a 0 or a 1. You cannot open it. Call the box F. 3 input bits means 8 possible inputs, and F has an answer waiting for every one of them. Now the promise. Either F is constant, the same answer on all 8 inputs, or it is balanced, 4 zeros and 4 ones. Your job is only to say which of the two it is, not to learn the answers. Constant or balanced? Classically, you have to ask, so ask 4 times, and suppose all 4 come back 0. You still cannot tell. The 4 you have not asked could all be 0, making F constant, or all 1, making it balanced. So the worst case costs 5 questions out of 8. Half the inputs plus 1. Add 1 more bit, and that number doubles. A quantum computer settles it with 1 question. To see how, we need 3 pieces. The first is the qubit. A classical bit is a 0 or a 1. A qubit is a unit vector in a 2-dimensional complex space, with the bit values as its basis. You never see the vector. You measure, and you get 0 with probability alpha squared, or 1 with probability beta squared. 3 qubits do not give 3 vectors. They give 1 unit vector in the tensor product. 8 components, 1 amplitude per input. So draw a state as 8 signed heights standing over the 8 inputs. Start the machine at all zeros, 1 spike and 7 empty slots. The second piece is what the machine may do. Every step is a unitary matrix. Unitary preserves length, so every step is reversible. The third piece is one particular unitary, the Hadamard, acting on a single qubit. It sends the basis vector 0 to an equal mix of 0 and 1. Apply it to all 3 qubits, and the 1 spike becomes 8 equal amplitudes. Every input is present at once, each with amplitude 1 over root 8. Not yet an advantage. Measuring here just picks 1 at random. Now the box. But F throws information away, and a reversible machine cannot. So the oracle keeps the input and adds the answer onto a 4th qubit. It maps x and y to x and y exclusive OR f of x. Run it twice and you are back where you started, so it is reversible as required. Here is the move the whole algorithm turns on. Set that 4th qubit not to 0 and not to 1, but to 0 minus 1 over root 2. If f of x is 0, nothing happens. If f of x is 1, the exclusive OR swaps the 2 terms, and swapping them multiplies by minus 1. So the 4th qubit comes out exactly as it went in, and f has landed as a sign on x. The answer was kicked back into a phase. 1 query, and all 8 amplitudes are signed at once, minus 1 to the power f of x over root 8. Measuring now would still tell you nothing. Every probability is still 1/8, signs and all. The signs have to be made to interfere. So apply the Hadamard again to all 3 qubits. On a basis state, it produces every state, each carrying the sign minus 1 to the x dot z. Watch only the amplitude of the all zeros outcome. Their z is 0, so x dot z is 0, every sign is plus 1, and the 8 amplitudes simply add. If f is constant, all 8 point the same way. They pile up to plus or minus 1, and the all zeros outcome is certain. If f is balanced, 4 point up and 4 point down. They cancel exactly, and the all zeros outcome can never occur. So, measure the 3 qubits. For our balanced f, every amplitude has collected onto 1, 0, 0, and that outcome is certain. It is not the all zeros string, so f is balanced. All zeros would have meant constant. 1 query and no chance of error. Try it yourself. Pick any balanced f on the 8 inputs, write its 8 signs in a row, and add them up. They cancel every time.